Hello, everyone, and welcome to another wonderful day of chemistry. So today we are going to be wrapping up chapter one, talking about gases by talking about corresponding states, which is more or less a way we can compare non-ideal gases of different identities in a little bit more of a robust fashion. So previously we talked about the van der Waals equation and how every single gas has its own specific A and B parameters. So again, uh, attractive forces and size that will really dominate its behavior. Well, it turns out if we're going to really kind of compare different gases across all kinds of pressures, volumes, and temperatures, one of the things that's really useful is we have a consistent reference point. Now, the problem is that there's not many points that occur on every single gas. There's pretty much two we can deal with, and only one we've seen so far. So the best reference point to use is going to be the critical point. So again, this is the temperature, pressure, and volume at which we can first make a supercritical fluid. So the nice part is every single gas has its own critical point, and it's going to be easier to hit that critical point if you have less intermolecular forces and are smaller versus if you're larger and have more intermolecular forces. So it turns out we can go ahead and compare the pressures against every single species by having what's called the reduced variable. And this is simply your actual pressure divided by the critical pressure. And so you can similarly, if you know the reduced pressure, back out the actual pressure. And you can do the same process for both a reduced volume and a reduced temperature. In each case, it's going to be the volume, often a molar volume divided by the critical volume, and a temperature divided by the critical temperature. So the nice part is both of these it's going to be easy to go in between the actual temperature and the reduced temperature, or volume or pressure, as long as you know the critical point. And every single gas has its own critical point. Now, something really impressive happens if we go ahead and compare different gases at the same reduced temperatures, volume, and pressure. And it turns out they replicate the exact same behavior. And we can see this by plotting isotherms. And that's what each of these lines are, is isotherms at a reduced temperature of 1, 1.2, and 2. So again, remember that um, the behavior should be more ideal at higher temperatures. So we're going to look at these isotherms as a function of the compressibility factor or the compression factor, so that's Z, versus the reduced pressure. So again, we're going to get more ideal behavior if the Z is equal to 1. And we expect as we get to higher reduced pressures to have more deviations. And we replicate the exact same behavior across nitrogen, methane, propane, and ethene, as we look at identical reduced pressures and reduced temperatures. It produces the exact same curve. And we can do this for a reduced temperature of 1.2 and 2. So in each of these cases, we see that we have identical behavior across all of the gases as long as we have the same reduced pressure, volume, and temperature. So all three of these will be essentially redundant. And this is amazing because it tells us that everything fits one equation. And as long as you're accounting for essentially the critical temperature, everything essentially plots the same, just different axes. And so this is actually a fairly impressive feature. And we can see this as we actually look at the various equations of state. So the ideal gas law, the ideal gas law and the virial equation don't run themselves to this reduced form quite so easily. But if we take the van der Waals form, which again is our first form that actually correctly mimics a real gas, we can go ahead and replace the pressure and volume with the reduced pressure and reduced volume to get a very similar equation with a factor of 3 that essentially pops up. And you'll notice that this also eliminates the A and B parameters. And that's actually because the A and B parameters are embedded in the critical point. So it turns out that we can show that for the van der Waals equation, the critical volume is just 3 times the size of the molecule, which makes sense because once the container is anything less than 3 times the size of the gas, we're going to see some really fun non-gaseous behaviors, and congratulations, we become critical. Similarly, the pressure term, the critical pressure, is essentially related to both the intermolecular forces and the size of the molecule. And the critical temperature, again, depends both on this balance of how repulsive the gas is, but also how attractive. And this is actually fairly impressive because what it means is that also, if I know the van der Waals parameters, I can correctly calculate my critical point, but also the flip. If we can identify the critical point of a gas, congratulations, we can obtain the van der Waals parameters. And similarly for the Berthel-Dirichlet and the other modified van der Waals equations. So this is actually fairly impressive because now instead of having to do more advanced fitting methods to determine our van der Waals parameters, instead, all we need is the critical point. So that's actually a really useful feature we can make use of. So that brings us to the end of our treatment of gases. And next time we're going to launch in to thermodynamics. Until then, take care.